Okay, we're live. You're welcome to ask questions, but if you do, you may show up on the internet. So, return, we're called RSV, return stack value.c, and here we'll want to be printing stuff, and so I'll include standard io.h, and here's a function, and we'll call it foo1, and it makes an array of size 2 on the stack and sets their values to be 3 and 4, and then it returns x. This is bad because we are returning an address that we will lose, that we should stop accessing when this function goes out of scope. And then we'll do it again. Here's foo2, and we'll set the values to 5 and 6. And then we'll have a main program, and we will say, we'll make a pointer 1 equals foo1, and pointer 2 equals foo2. Now let's just stop right here and print these pointers. P1 equals %p, and P2 equals %p, and then P1, P2. Now, I want to comment. I've been programming for 25 years. I can write this much code and then compile it, and there's an okay chance that it will compile and run and do the thing I want. For everyone who's just starting, you should be looking at writing more like 2 or 3 lines of code, compiling plenty of print statements and confirming it. And if you write a bunch of code, and I see this every year, someone gets a problem, it inspires them, they work out on a notebook how to do it, and then they go and translate that all to code, and it's 100 lines of code. That is a bad plan. And I understand why people want to do it, but it does not fit like effective programming. Because first off, you write 100 lines of code and you try to compile it, it doesn't compile. But then once it does compile, it just takes forever, because once you start getting 3, 4, 5 bugs they're compounding, it's just impossible to figure out. So this is an anti-role model to write even this much code, and this really isn't very much. rsv.c, and so I did have no compile errors, but I got the 2 warnings. So the compiler in this case is able to figure out I shouldn't do it. And if I run it, so this is exactly what I thought would happen. P1 is some memory location, and we got used to looking at these memory locations on Tuesday, and we realized that everything was kind of the same at the beginning, and so P1 is ending at 6.0, and P2 is also ending at 6.0, right? So when we called foo1, a reservation was made on our behalf for 8 bytes, and when we exited foo1, those 8 bytes were reclaimed. When we called foo2, we made another reservation for 8 bytes. In this case, what was returned was the exact same 8 bytes, right? So as we're writing 5 and 6 to those locations, then we're certainly overwriting the previous 3 and 4 there, okay? What we're doing again is we're writing to locations we never should have written to in the first place. So let's start by doing this. And then where I felt I did a poor job explaining was at this step right here. So if I say P2 of 0 is %d and P2 of 1 is %d, I said a poor job of explaining on Tuesday, and we do this, I actually think we're going to get the right thing, because we placed 5 and 6 in those addresses, and probably no one overwrote them, because what could have gone wrong in that little amount of time? Right now. Sorry. Hey, look at that. Well, we'll turn off that feature. I thought we'd get closed caption. We won't. So we'd say, what could go wrong? Actually, this will go wrong. So let me start. Let's do it this way. I'm going to take out this print statement. And I think with this right here, foo2 has returned P2 and we print it immediately. I believe we're going to see 5 and 6. Okay? So we're going to compile it and run it, and we do see 5 and 6. Okay? But if we go and this is what I thought I could have done a better job explaining on Tuesday. If we take this out right here, now we know that we're not messing with these locations, but if we compile and run this, we get the same addresses we had before, but P2 is no longer 5 and 6, right? Something changed. So when we commented out this printf right here, we got 5 and 6. When we add it in, we don't. And the reason why is because printf is also using these locations. So when we went and, for example, allocated these two ints, we were certain addresses, printf is using those same addresses because they're temporary addresses. We're not supposed to still be accessing them, okay? And then so that's why this print statement right here changes the values of this print statement right here. Now the last thing I'll do is I'm just going to show that if the very first thing we do is print out P1, we'd get something close to what we expected, which is that we put 3 and 4 in those locations, foo2 overwrote them with 5 and 6, and so when we're trying to print out what we think of as the return value from foo1, they're overwritten and become 5 and 6. So that would be the thing we would have expected to happen if we would have done it first. Okay, yes, Spencer? Correct, let's do that experiment. So if we don't, by the way, I see this all the time where people are up here and they want to get down below, and then I just see them, they do this and they're going down like this with the cursor. I don't do that. So here I am at the top of the file. Here, let me start over. Here I'm at the top of the file. I just search. You see, I did a slash to search, and I search for foo2. There it gives me that one. I search again, and I'm there, right? And then I want to take out this line. I would do a Shift-I to get to the beginning. I guess that's C++ style. And so, a lot of the magic of VI is navigating through the file very quickly. Okay, so then to answer Spencer's question, if we do this and we run it, we get 3 and 4. And this is actually a really terrible thing, right? Because what it means is if you're following the playbook I'm asking you to follow, where you write a small amount of code and then you compile it and add print statements and test it, it looks like it did the right thing. And it is the right thing until someone goes and overwrites it. Does that help? Any other questions on this? Yeah, Nathan?
What if we have P1, it's allocated to this, P2 is allocated to the same block.
Yeah.
If we had a variable in between those, like we say I is these 4 bytes, and then we allocate space for P2,
yeah.
Not pointing to the same place?
Well, the question was, because I don't think that's going to show up very well, so let me try to just summarize the question. I'm not going to summarize exactly as you did. If we go and there's additional allocations, then could it change the behavior? And the answer is absolutely. Possibly positively, maybe not. And so getting extra stuff in there, is just gonna make it run differently. But the takeaway is, if there's places that you're not supposed to be writing or reading, don't do that, right? And so when you do an allocation, you've done, for example, a malloc, you own that, and no one else should get in there, and you shouldn't get into anyone else's business. And similarly, if you have stuff that's on the stack, the automatic memory, it's only good for the scope of that function. So yes, there's lots of ways that you can add more allocations in between and kind of defer the problem, but really the best thing is just not to go there. Okay.